Yes, we are good to start.
Awesome. So, Nandeep, I hope you can hear me. And is my screen visible?
Yes, we can hear you, we can see you, and your screen is visible. All perfect. Yes, thank you.
Awesome. Thank you. So, hello all. Uh, Thanks for joining the call. And before I begin the presentation, let me quickly introduce myself. My name is Abhinav Bohra. I work at Amazon Advertising as a applied scientist. I have been in Amazon for last 7 years and been in the data science AI space for last 10 years. And today I'm here to share one of my experience with data information retrieval. That's what my key forte is in. And I will be sharing how information retrieval could be done more efficiently. And when the scale is large, how can we make use of LLMs to do information retrieval at a large scale? So, yeah, before wasting more time, and why don't we start with the presentation? So, the topic for today is self supervised structured extraction at a billion product scale. So, the key goal is not only introducing with like usual information extraction task that we do in the industry, but rather providing a way to do it more scalable at using LLMs. So, basically, when I started working in this area, I started noticing that whenever we try to build something which is a prototype, which is our first product out, it looks good on the test data set end, where we see that, okay, the performance is good, the accuracy is high, and the results look good on papers. But whenever we try to bring those models, those LLMs into production, we face roadblocks. And the roadblocks could be related to latencies, cost, and multiple other things that could come up while we are bringing the LLM into production. So, yeah, in today's talk, we will be going over how can we solve some of those problems related to specifically related to latency and cost, and we will be covering representation, self-supervision, distillation, and inference, where I'll be introducing a concept called parallel decoding and how can we perform that concept. All right. So to begin with, let's see how why the quality bar whenever we try to do production deployment and try to bring our model in production, why they fail. So basically, whenever we use frontier LLM, let's begin with frontier LLM. Whenever we try to use frontier LLM for any of the use cases, there is a definite blocker that it's not acceptable in production due to the cost and latency associated with the frontier LLM. So, right on our mind, we think that, okay, what could be the next potential solution? We think of distillation. How can we uh, train a smaller LLM model? But again, when we are thinking of training a smaller LLM model for that purpose, still there could be a couple of challenges. For example, challenges related to the scale. Let's say if we want to run a smaller LLM model at a billion product scale, where you have billions of samples that needs to be processed through the LLMs. Now, in that case, even the small language model would not work or might be challenging because then you would need an army of GPUs to get your results out, and that becomes difficult when we are working under tight budget and tight deadlines. So and yeah, to so in this these are the challenges that our team was facing and we were trying to solve it. And one another problem that we often see is whenever we have context, the context is usually available in textual format and tabular data. So whether it's any type of model that we are working with, whether the model could be classification, retrieval, forecasting, ranking, we try to provide the entire context to the model in form of, if it's textual data, then the entire textual data goes into that model. And the textual data in multiple industries like e-commerce, healthcare, and multiple, like manufacturing. The textual data could be a lot of data. There could be around 5,000 to 3,000 tokens on a single product, which are basically the fields which are used to describe those products, the attributes used to describe those products. And if you collect everything and feed it into those model, they could include noise. Those data sets can have noise and a lot of information which will drift away the focus of the model from the key values that that data set pursues. And if, let's suppose, you have 10 to 15 model running in different teams in your organization, then if you provide the entire data set to each model, we are basically introducing noise to each and every model, and we are adding additional tokens, which later reflects in terms of additional cost, latency, budget issues while deploying those models. So this is a foundation problem, and that could be noticed in multiple teams and organization on how they deal with data and how they try to process that data. That being said, here's an example that I'm sharing where, let's suppose, if you are looking at an e-commerce data set, and there could be different product categories in an e-commerce data set. So let's say there is footwear. Now there could be very personalized features for footwear, like attributes for footwear. It could be fit type, it could be size of your shoe, etc., etc. And going on with the electronics, the attributes could be very personalized as per the electronic industry, which could include connectivity, power, and how much time does it take to charge your electronics, those kind of attributes. So now if you start collecting all these attributes per product category, then you might end up with thousands or millions of attributes, because there could be multiple product category available in an e-commerce industry. So now when we think of extracting these attributes, we think of LLMs. Now imagine if we are using LLMs to extract these attributes per product category, then there could be multiple challenges associated, such as hallucination, how these attributes are extracted, and are these attributes uh, are even correct for that product category, and how are we going to support these attributes in our database tables. Because if there are millions of attributes, some of the attributes would be sparse, they won't be available for all the product types. So in these kind of challenges we encounter. So that being said, there is a way in which we can solve a couple of problems that we discussed by using a representation layer. So basically what we do, we try to collect all the content that is available for a product and try to summarize them in form of a JSON. Now, when we summarize this in form of a JSON, we make use of LLMs, and we try to introduce a schema. So this JSON, you can consider it as a schema, that for every product type, we will have a schema, and the schema would include the different attribute and value features for that product type. And why we are doing this? We are doing this to tighten the teacher-student distillation that we will be discussing ahead, on why we need a schema and why how the schema helps us with the teacher-student distillation and inference we will be discussing. So what we are doing over here, we are basically converting all the data of each unique product into a form of a JSON schema. So it could be later on used for downstream models. So how it works, when we begin with, let's suppose we are dividing this into two categories. The top category is the offline process, and the next category is the production process. So when we see the offline process, the first step is we collect the data, and the next step is we generate dynamic schemas. So as we already saw in the previous slide, we were generating those dynamic schema, which are JSON from product text. We do it for every product category, and then we do a teacher model training, a teacher model information extraction. So let's suppose in our case, the teacher model could be a Claude model, a Claude Sonnet 4 or 4.5, which is generating these schemas for us. So, and once these schemas are generated, we verify those schemas, and using again Claude as a judge, and then we perform distillation. So with distillation, what we are doing, so the Claude model learned through based on simple prompt engineering that, okay, for a certain product type, here are the top key attributes that we are interested in, and what are the value for those attributes. And once we have identified those key value pair, we do distillation where a small LLM model is trained to perform the same task. Now, what are the key blockers that we face in production in such use cases is that the scalable inference. So now when we come to the next, the bottom one, the production extract across the catalog layer, here you would see that the compact student model, while at the inference stage, it needs to run on a daily cadence. And the reason for running on a daily cadence, because the product information could change and we need to revise all the products and their key attribute value pairs on a daily or maybe a weekly interval to make sure that we are up to date with whatever information is available on a product across the globe. So to do this, uh, to solve this problem, there could be like one approach we already discussed is distillation. That instead of using a frontier teacher model, which could be Claude or GPT family, we will train a distillation and we'll do distillation and train a compact student model, which could be from families like Quen, Mistral. And once that model is trained, that solve our one of our bottleneck, and that is we cannot use frontier model because of the cost related problem. And the distillation is performed using two specific techniques. One is LoRa and another is CLORA. These are like low rank adaptation techniques, which reduces the matrix used for representing those product and basically adding like two key metrics to the existing matrices available. And then we do distillation. So during distillation, one of the key technique is a standard autoregressive loop in which we predict one token and it provide the feedback to predict the next token. So all the token generation that happens one after the other. So for each token prediction, which is a probabilistic prediction, the previous context is provided to the model. So now if we keep on predicting one token at a time, which is a standard way of how LLM runs its inference and does the decoding, it's very time consuming because we are doing one after the other token prediction. And and if let's suppose your scale is very high, then you might face challenges during the inference. So to solve this problem, we started making use of parallel token prediction. So, and we are able to do in this case that instead of doing one token at a time, we are parallelly predicting the tokens for each attribute value pairs. So, for example, uh, let's say you for a certain product like iPhone, there are 10 key attributes where it could be like screen size and maybe the battery life, etc. And then there is product context, what is like whatever the context is available about that iPhone in a form of long unstructured text. Now from that unstructured text we want to generate what are the key attributes for iPhone. So instead of doing one token at a time, we can do this parallelly and generate four fields out of it parallelly instead of one token, which makes it very faster. And the speed, like the latency drops by 21x with this process. So how it is done is whenever we provide it a JSON schema while creating these attributes, we will attach over here a special token before the value proposition. So first, the special tokens identify the product block and the JSON that was used for the schema generation, and the value start proposition. And the second, we assign separate position ID ranges to different attribute values. So basically what happens, this prevents the value from being treated as a continuous position sequences. And we apply a 4-dimension attention mask where every value can attend the complete product prompt and shared schema. So by doing this, each key is able to attend to its own attribute key and previously generated tokens. So as you can see in this image, each field we are doing first token generation, and then we are doing T1 and T2. So how it works, that it performs a full forward pass over the product information and schema, and that pass produces the first token for every attribute value. And the prompt KV cache is retrained. So later on, the iterations pass only the new generated value tokens. And the product context is not recomputed at every step. Some values finish one after or two tokens, but all other require more decoding iterations. And the speed up, what we noticed with this technique of parallel decoding is that instead of doing 100 sequential value token steps, we only need to do 5 to 8 decoding iterations. And yeah, and using these, we also compared that, okay, is there, while improving the performance, what about the quality and reliability? So we checked it on like 5 parameters, which included accuracy, hallucination, parsing stability, and the length of the fields. Like the length of the field is not changing substantially because instead of doing sequential generation, we are doing parallel now. So it was consistent, and that gave us confidence. And yeah, so this covers my entire slide presentation, which includes like the first, the representation that we covered. And the second one was supervision, which was dynamic schema generation. The third one was distillation, where we trained a LoRa model. And the fourth one was the decoding, where we do parallel decoding to speed up the inference. I'll stop myself over here and see if there are any questions.